Hello, everybody. It's 2 minutes past 4, so we'll get started. Today's guest for the combustion webinar needs no real introduction, but I'll do my best. It's Jacqueline OConnor from Penn State University. Jackie OConnor is an associate professor of mechanical engineering at Penn State University, head of the Reacting Flow Dynamics Lab. She's also the director of the Penn State Center for Gas Turbine Research, Education, and Outreach. And today she is going to tell us about methods of combustion instability suppression and outlook for combustor design. Should be an exciting talk. Before we get started, I'll just let the audience know that if you have a question, just write it in the chat box and I'll collect them, and then we'll try and run through as many as we can towards the end of the lecture, and that way we'll be able to keep on time and get to as many questions as we can. So with that, the floor is yours, Jackie, and take it away.
Thank you so much. Well, thank you everybody for coming today and for inviting me to give this seminar. It's very nice to share your Saturday with you wherever you are in the world. So today I'm going to be talking about combustion instability or thermoacoustic combustion instability. And in particular, we're going to be talking about methods of instability suppression. When I was putting together this talk, I thought about the audience. And so I don't think I need to convince this crew about the importance of combustion devices. And so I'm just going to dive right in and start talking about the good stuff. What I do want to do first, though, is talk a little bit about how combustion instability works. I understand the combustion community is a broad group of people, so I want to make sure everybody's on the same page. So if you're familiar with thermoacoustics, just bear with me for about 5 minutes here, and then we'll get into the more research-based stuff. So when somebody gives a talk about thermoacoustic combustion instability, it's obligatory to show pictures of hardware that's been damaged. Combustion instability, or sometimes referred to as combustion dynamics or combustion oscillations, is one of the most expensive problems in the gas turbine industry. It's also prevalent in rockets, both liquid-fueled and solid-fueled rockets. You see it basically anytime you put a flame in a box. So big process furnaces can have instability issues, water heaters can have instability issues, and we'll talk about the feedback loop that drives the instability in just a second. The main motivation, though, is that in its extreme form, it can cause catastrophic damage, like you're seeing in these two pictures from a really nice edited book by Lewin and Yang that describes a lot about combustion instability. But the main reason, this doesn't happen very often. I was kind of kidding about, everybody showing these pictures. This is not the main outcome of combustion instability. Really, the main outcome are these last two bullet points: reduced operability and increased emissions. You get instability because you're trying to run your combustor to reduce emissions. So if you've put all this effort into creating a low NOx combustor that then is unstable and creates more NOx, that's sort of counterproductive. But the real issue is operability. So operability is really, I kind of define it as how well your engine operates, how easily your device is operated. And so if you have these pockets of instability around your operating range that may move depending on the weather, the season, the fuel type, the humidity, if there are gnomes in your fuel system. I mean, I'm kind of kidding, but there are, about the gnomes at least, but there are a whole host of issues that can change the sort of how an instability manifests, the frequencies, these sorts of things. And if you're trying to track this moving target, it really increases the complexity of operating your machine, and as a result, reduces what we call operability. All right, so let's get into a quick review about what drives thermoacoustic combustion instability. So it's a self-excited feedback loop between flame heat release rate fluctuations and combustor acoustic fluctuations. So what's happening here? Let's say you have some perturbation to the flame and it causes an expansion. I'm teaching thermodynamics right now, so we all remember that expansion does PDV work or expansion work on the surroundings. And that PDV work, if it's aligned with a portion of the acoustic field correctly, so where the acoustic field is susceptible to forcing, then you can transfer energy from the flame into the acoustic field. Now you have an extra energetic acoustic field that creates more perturbations that drive more flame heat release rate oscillations that drive more energy into the acoustic field. And you go around and around and around. Combustion instability is really a phenomenon that I think is better heard or felt than analyzed. If anybody's been in a room with an unstable combustor, they're quite loud. And it's, I don't know, it's kind of an exciting experience. So one of the combustors that we're going to talk about in today is one in my lab. This is a 5-nozzle can combustor. And I'm going to play a video. I kind of hope you'll be able to hear the sound. We'll see. What you're going to hear is a tone on top of the turbulent noise when the word on top says unstable. And then we're going to do something to the central nozzle. We're going to add more fuel to the central nozzle. The word on top will change to staged stable, and I'll explain what that means in just a second. And the tone will go away. It'll still be noisy, but it won't be tonal. So let's see if this works. So there's the tone. There's the staging. All right, and the tone goes away. So for that particular combustor, when it's unstable, it's about 115 decibels in the room. That tone is about 520 hertz. If you're a musician, at least in the United States, your orchestra tunes to an A440. And so it's really quite a nice tone, but it's extraordinarily loud. And this is just an atmospheric, research combustor. You can imagine in an actual engine that these pressure oscillations can be a lot louder. In actual devices, the feedback loop isn't just the flame and the acoustics. There's typically also a coupling mechanism in the middle there. And so this is some other type of perturbation, typically in the flow, that is driven by the acoustics that then links the acoustics to the flame heat release rate oscillations. There are a bunch of different types of coupling mechanisms, but the one that we're going to focus on today, which is the focus of a lot of my research, is velocity coupling. So this is where the combustor acoustics drive some sort of velocity fluctuation in the flow field that then drives flame heat release rate oscillations. So a really nice example of this came from an experiment that we did years ago. This is a really low Reynolds number. What you're looking at here are high-speed particle image velocimetry images. Let me grab a pointer here. Okay, flows going from bottom to top. There are 3 triangular bluff bodies. I've put them here in blue. And basically you can see the flame is the interface between the bright area and the dark area. We've seeded the flow to do PIV, and because of the gas expansion across the flame, you get, a much lower particle density in the products than you do in the reactants. We're acoustically forcing this system. So to see how the flame responds to acoustics, we're forcing this at 400 hertz. And the Reynolds number here, based on bluff body diameter, is something like 3,000. It's quite low. But that means that we have not too much turbulence, so we can see the coherent wrinkles very nicely on the flame. And what you can see shedding off each of the edges of the bluff bodies are these vortices. These vortices are being excited by the acoustic forcing coming from the base of the experiment. You get this nice coherent shear layer roll-up due to the coherent excitation of the shear layer. And then you can see the flame basically wraps around these vortices, and these wrinkles grow and change and merge as you go downstream. So if you imagine that for a premix flame like this, the flame heat release is proportional to the area of the flame, so the amount of surface where you can convert reactants to products, then by modulating the area of the flame using, these vortices, you end up modulating the amount of heat release. And again, this goes back to the thermoacoustic feedback cycle. So for more details on this experiment, we have a paper in Physics of Fluids that talks a lot about the natural dynamics of these flames, which are kind of fun. This is a really low Reynolds number, right? So Reynolds number 3,000 isn't particularly relevant for most combustion devices, But that combustor that you just saw in the previous video with the sound, this is the high-speed chemiluminescence imaging of that combustor. So you can see there are multiple flames. Here's the one on the left, the one on the right, and then the one in the center looks bright because you're actually looking line of sight through 3 flames. But this is really turbulent. This has a nozzle velocity of 26 meters per second. You know, swirl and all the types of realistic features that you'd see in an actual engine. And you can still see, you know, coherent flame wrinkling at the instability frequency. So this is the self-excited instability. So this flame is wrinkling and pulsing 520 times per second. So, you know, this again is a result of this velocity coupling. I don't have PIV data here, but based on a whole bunch of other stuff, we were able to, you know, isolate the velocity coupling mechanism in this combustor. And for more information on this particular study, you can go to this paper down here. All right, so those are the basics. And so for the rest of the presentation, I want to talk about how we use our fundamental knowledge about combustion stability to inform how we do instability suppression. And so we're going to return to this bubble chart a few different times. And we're going to talk mostly about 2 different categories of suppression, but I want to mention one common one first that we're not really going to dive into, and that's just acoustic damping, right? If you have an acoustic mode inside your combustor, you can reduce the level of acoustic fluctuations by adding acoustic damping to the system. This is typically done by adding a resonator, either a quarter wave tube or a Helmholtz resonator, by putting perforated plates in the system. Perforated plates are great acoustic dampeners. And there are people much more qualified than me to talk about the details of acoustic damping in combustion systems. And if folks have questions later, I can point them to some excellent resources. There's an issue, however, with acoustic damping, which is that it's typically focused on a particular frequency. And like I mentioned previously, if you have, sorry, my little pointer here is kind of freaking out. Sorry. Okay. If you have an instability that is changing frequency, that is changing, well, mostly frequency as you change, again, season, fuel composition, humidity, weather, gnomes in your fuel system, whatever it is, then your acoustic damping also has to be able to change with those. And again, it increases the complexity of the operability if you have to like continuously tune your damping system. Some types of resonators are tunable. So quarter wave tubes and Helmholtz resonators can be designed to be tunable. Things like perforated plates aren't tunable, right? And so even though acoustic damping is used ubiquitously, it's not the most robust way of suppressing instability. There is also a very large and extremely interesting literature on active control. I have myself done some work on active control. We're not going to talk about that today, but I can answer some questions afterwards if people have questions. What I'm particularly interested in this talk is how the mechanisms that are commonly used in industry work. And then also how we can better think about combustor design in the future to suppress instability. So the first of the 2 buckets that I'm going to talk about are suppression of instability by minimizing global heat release rate oscillations. And there are 2 different ways that this is typically done in industry engines. One is called fuel staging and one is called piloting, and we're going to talk about both. So the first one we're going to talk about is fuel staging. Fuel staging is used in multiple combustor configurations, but the one that we're going to talk about today are can annular systems. So these are like the big heavy frame gas turbines, where in each can you have multiple fuel injectors. And these fuel injectors typically are hooked up to multiple different fuel circuits. And so this example comes from a really nice report by Davis and Black out of GE about their DLN dry low NOx 2.6 injection system. They have 3 fuel circuits in their can annular systems. And so they can change the amount of fuel to each of the nozzles independently, keeping the global equivalence ratio constant, but sort of unbalancing the fuel, and this helps suppress the instability. So one of the experiments we have in our lab, and this is the video that I showed you before, is sort of a representative geometry of these can annular systems. It's called a 4-round-1 combustor. So there are 4 nozzles on the outside and 1 in the center. You can see this is the top view here. They have swirling flow injectors here. And we can either have a pre-mixed mixture of natural gas and air come into this manifold and split, or we can put the fuel directly into the nozzles like they were designed and have a partially pre-mixed mixture. This experiment's really cool because it's optically accessible. So this is what it looks like in the laboratory. So these are the 4 nozzles around the center one, and we have this big 10-inch diameter piece of optical grade quartz around it as the combustor liner. So we're capturing a lot of realistic flow features in the combustor by having, interacting flames. The spacing is based off what you'd see in typical combustors. What we're not capturing here is the pressurization that you typically see in a combustor, but we trade that off so that we can see inside and have a really nicely optically accessible experiment. We changed this. So this experiment was originally built by my predecessor at Penn State, Dom Santafica, and I inherited it when he retired. And so I'm extraordinarily grateful for that. One of the things that we did in this experiment was we added a solenoid control valve to different fuel circuits, so we could change, as we were doing the experiment, the amount of fuel in a given nozzle. By adding fuel to one nozzle, it would decrease the equivalence ratio in the other nozzles. So we're maintaining the global equivalence ratio. And so we could look at the effect that staging had, so this unbalancing of equivalence ratios on the instability. Okay, so this is just a quick overview of how staging works. So here I'm showing you on the x-axis overall global equivalence ratio for the combustor, and on the y-axis is the pressure fluctuation. This dotted line is how we define unstable for this system, which is 0.5% of the total pressure inside the system. And so if we fuel all nozzles equally, so those are the blue dots, as you increase the equivalence ratio at an equivalence ratio of about 0.7, this thing really starts to scream. Like I said, by the time you get up here to 0.7, 0.71, it's about 115 decibels in the room. It's extremely unpleasant. My colleagues really hate when we run this experiment because you can hear it through the entire building. We have to run at night so that people don't get mad at us. So what we're showing in the 2 other dots here, if we take 1.4% of the fuel and we add it to the center nozzles, subtracting it from the outer nozzles, that's 1.4% staging, it doesn't really do much. But if we take 4%, these are the magenta dots down here, we can get up to much higher equivalence ratios, but have basically no instability whatsoever. So less than 5% of fuel displacement to a staging nozzle gets us in suppression of the instability, which is pretty neat. Okay, and one other thing that I'll say here is this when we first did this characterization, we're pretty psyched about this because real gas turbines display this behavior, right? They use fuel staging to suppress instability with 5% levels is not unreasonable. And so the fact that we could mimic that behavior in a laboratory combustor was a good thing. Okay, so then we used 2 different diagnostics to understand what was going on here. So the first one is high-speed chemiluminescence. So we have a high-speed camera with an intensifier on front. We're looking at CH star, so we're filtering at 430 nanometers. And we take high-speed video. So you saw that high-speed video earlier. On a pixel by pixel basis, we take a linear spectrum using a fast Fourier transform. And then at the instability frequency, which is really evident by either standing in the room or measuring the pressure inside the combustor, we can pull out the data at that instability frequency, and we can plot the RMS of chemiluminescence and the phase of chemiluminescence at that frequency at each location. So this is what an RMS image looks like. You can see that high levels of oscillation are at the base of the flames, at the here where the flame's running into the wall. So it, sort of quenches really quickly. So you get a high RMS level. And then at the top where you have this pulsing, and so the flame height is changing a lot in this region, which is why you get high RMS levels. This is the phase. It doesn't really, phase is only interpretable if you're comparing one phase to the next. So as you go downstream along a flame, you can see you get, if you look at this color bar here, you get a nice phase roll off, which is indicative of a convective phenomenon along the flame. So this is the flame wrinkles that we saw in that high-speed video convecting downstream. And if you kind of stare at your phase Rorschach test long enough, you can interpret what's going on. It takes a little bit of training, but eventually you get used to looking at these things. All right. So one of the things that we found was that, we looked at these RMS and phase images for unstable and stable cases. Phase doesn't have a whole lot of meaning when your amplitude is really low. And this is true not just for chemiluminescence, this is true for any FFT. If your amplitude is very low, then your phase is basically meaningless. And so, you're getting a lot of random numbers and kind of patchy things here. And that's just because the data is not really all that meaningful. But in the regions where you have slightly higher RMS, you do start to see structure in your phase. And that's in part because you're getting, enough signal to be able to interpret the phase. Basically, what this is saying is that, when we don't have an instability, you don't have this coherent motion, so you don't have coherent phase coherence between the flames. So the other thing that we wanted to do to understand more about the specific dynamics of what was causing the instability to be suppressed, we went through and we used high-speed OH planar laser-induced fluorescence. So we shoot a UV laser through the combustor. This first window, these are 3 windows of lasers that we took. These videos are not simultaneous. Each window is about 1.5 inches to 2 inches tall. We target a transition on an OH line, and then we collect the fluorescence from that transition. And the way you look at these images is the flame for premix flame is the edge between the light and the dark. So this flame over here is the rightmost flame on the experiment. This one is the center one. And you can see in the middle, the corner, or over here, the corner recirculation zone, and then these smaller recirculation zones that show up between the two flames, 2 adjacent flames. What's really cool about these images is that you can see the coherent and turbulent wrinkling. So this guy's a little bit brighter, the laser's coming in from right to left, so you're losing photons as you go across the screen. But if you look at this right one, you see this pulsing, out and in, the flames going out and in and out and in because of the vortex shedding. But then you can also see the really fine scale turbulent wrinkling on the flame as well. So one of the things we were curious about is, as we were staging the combustor, what's actually causing the instability amplitude to decrease. And so to understand this, we tracked the edges of this flame and this flame, so the center flame on the left and the right flame on the right, to understand the coherence between the oscillations on each of the flames. So we looked at 3 different cases. The first case was unstable, and so that was the video that you were just watching. The third case was completely stable. When you do staging through the center nozzle, this combustor becomes very stable. There's no tone. You can see this is pressure as a function of time. Very, very small amplitudes. The right nozzle in this experiment is a little wonky. We think one of the welds is a bit busted. And so it's not that good at suppressing the instability. It's not that it's off center. We tried the left nozzle and what we called front and back, and those suppress the instability perfectly. Like I said, it's just some weird feature of the right nozzle that means that it doesn't suppress the instability quite as well. But this was actually quite lucky, right? Because we could get this kind of metastable situation where we had enough amplitude to be able to look at phase information, to be able to look at coherence, but it was much lower amplitude than the unstable case. So this is one of those places where a weird quirk in your experiment can actually be really helpful. So the way that we quantified coherence was by tracking the flame edges. So we took the mean flame location and tracked the lateral displacement of the flame as a function of downstream distance. If these two flames are fluctuating coherently, that means they're going in and out together. But if you have a single coordinate system, it looks like their phase will be 180 degrees apart. And so having we're going to plot this phase as a function of basically pi radians, where pi is in phase or coherent oscillations that would be indicative of instability. So let's look at the unstable case. So this is a video. We have everything staged equally. As you go downstream and you look at the center nozzle, which is this guy, and the right nozzle, this is the phase of that lateral fluctuation as a function of downstream distance. And you can see that they're almost pi radians apart. And so this is indicative of really coherent unstable oscillations, which is what we expected. If you go to the perfectly stable case, here you can see the video. The flames are just sort of turbulently bubbling away. The phase is just a bunch of nonsense, which is what we expected because there's no coherent oscillations. But if you look at the metastable case, this one was really interesting. There's still enough coherence such that the phase, so these are the blue dots, the phase isn't nonsense, but now they're closer together in phase, which means that they're actually dephasing from each other. And so from this, we developed a hypothesis, initially from the chemiluminescence imaging, and sort of clarified it using this, that one of the things that staging does is it dephases the oscillations of one flame relative to the next, so that they are destructively interfering with each other. And you are now the nozzle that has all the fuel is destructively interfering with nozzles that have less fuel. And so your instability amplitude comes down as a result. And we were able to look at this in a lot of detail using this high-speed planar laser-induced fluorescence. All right, so another way that we can reduce flame sensitivity to perturbations is through using what's called a pilot flame. And so a pilot flame is basically now you have two fuel circuits in a single nozzle as opposed to multiple fuel circuits in a combustor. This video, the reference that I'm going to be talking about is a paper we published that came out earlier this year. On the left is an unstable swirl stabilized flame. You can see really nice oscillations coming out of that. And then on the right is a piloted flame. So this central jet flame in the middle is the pilot flame, and it suppresses the instability. It doesn't always suppress the instability. Actually, we're writing a paper right now about when it doesn't and why it doesn't. But for the most case, piloting can be really effective at suppressing instability. And the goal of this work was to figure out what the actual mechanism is by which this is happening. So I have to give a lot of credit. The first half of this study was done by a student, Ji-Hong Lee. Ji-Hong was Dom Santifica's last PhD student. This work was funded by Solar Turbines. We worked really closely with Jim Blust and Michael Akiki on both the earlier work as well as the follow-up that we did that I'll talk about in just a second. So Ji-Hong designed a really, really clever experiment. So what he did was he sort of modified the fuel injector so that he could change both the pilot flow rate as well as the pilot equivalence ratio separately. what this chart shows a lot of things. On the x-axis is what I'd pay attention to is the equivalence ratio of the pilot flame. The equivalence ratio of the main flame here is 0.6. And as you increase the equivalence ratio of the pilot flame, you reduce the level of pressure fluctuation inside the combustor. And the way he's increasing the pilot equivalence ratio here is by increasing the fuel flow rate in the pilot. He does it the other way as well. Here, he is increasing the airflow rate of the pilot, keeping the fuel flow rate constant. So now equivalence ratio is decreasing from left to right, and you basically get the same result. So higher equivalence ratios in the pilot give you lower instability amplitudes. And it doesn't matter how you do it. You can either reduce your fuel or increase your air, you get the same effect. So one of the things he was really interested in was, okay, what seems to be controlling the efficacy of the pilot here is not the flow rate so much as the equivalence ratio. So then what he did was he took data at a whole bunch of different pilot flow rates, which is what's on the x-axis, and then a whole bunch of different pilot equivalence ratios, which is what's in the colors, and measured the acoustic fluctuation in the combustor. So this dotted line across the center, this is basically the no pilot condition. And so anything above here is the pilot making the instability worse. Anything below here is the pilot making the instability better. And what's really fascinating about these results is two things. One, the equivalence ratio at which the pilot makes things better. It starts at about a pilot level of 0.55 and 0.6, remembering that the main flame equivalence ratio was 0.6. And as you get to these places, to these equivalence ratios where the pilot is effective, the pilot flow rate is basically not an issue, right? You get the same level of suppression essentially for a whole bunch of different flow rates. So even though some of these pilot equivalence ratios are rather high, like 0.7 as compared to a main flame of 0.6, somebody might say, NOx, right? Like I'm running this little rich zone in the middle of my injector. But you can run very small amounts of fuel through that pilot and still get the same level of efficacy as a whole bunch of fuel and still get your pilot to work. So this is such a clever design, and I can take no credit for it. But when I took over, the lab, this data was kind of sitting around, and we thought, wow, this is a really good test case for understanding more about how the pilot is working. Because what this suggests, this experimental result suggests, is that the efficacy comes from the equivalence ratio, not from the flow rate. So we partnered with my colleague, Yuan Chuan, who does high fidelity simulation, and Michael Akiki, who is one of the engineers at Solar Turbines, who's really in charge of their LES efforts. And so we did a simulation of the injector at a bunch of different operating conditions. And so this is the condition with no pilot. This is the condition with lean pilot. And then this is the same condition. I should have put these on the slides now that I'm looking at all this. This is the same flow rate, but with a pilot that has the same equivalence ratio as the main, or sorry, a slightly higher equivalence ratio than the main. And then this is the high equivalence ratio, but a high flow rate. So you can see on the bottom is temperature, on the top is the time average flow field. This pilot jet extends just a little bit here out to about a distance of 5 centimeters. This pilot jet extends out to about 8 centimeters because this is the higher flow rate than this one. So what we're plotting on the right over here is along these lines. This first line here is the plots I've put over here. We're plotting temperature as a function of radial distance, and then mole fraction of OH as an indicator of a reactive combustion species. In the paper that I showed reference where this came from, we look at other species as well. But one of the things you can see, so the baseline is the dotted line, that's no pilot. The lean pilot, which is 0.2, actually cools the region behind the main flame, whereas the pilot that's just a little bit richer than the main flame actually heats it up. And you can see that in these temperature profiles here, as well as the cuts here. Similarly, with the lean flame, you're kind of starving the recirculation zone of active radical species, whereas with the slightly richer, you are giving them a boost. And as you can see between the blue lines and the green lines, you get the same effect regardless of pilot flow rate. And so what we showed in this study, and again, there's a lot more discussion and more data in the paper, was that essentially the pilot, we can see, we also did a bunch of lift imaging later. The pilot doesn't directly interact with the main flame. There's no like intersection of the flames. It's not a direct sort of stabilizing mechanism. What it's really doing is back supporting the main flame. And again, if folks want to talk a little bit more about back supporting, I love talking about this. It's a really interesting subject. But basically, you're sort of wrapping the flame in a warm, insulative region with slightly higher temperatures and a lot of active radical species. That helps both the static and dynamic stability. It basically makes the flame less sensitive to perturbations, and so reduces its susceptibility to acoustics and suppresses the instability as a result. Okay, in my final 10 minutes here, I want to talk about one last way of suppressing instability. The methods that I've mentioned so far are ones you see in industry all the time. Most gas turbines, lean premix type systems will have acoustic resonators on them. And the use of fuel staging and piloting. Not all pilots look like central jet pilots. Some of them are rings, some of them, there are a lot of different designs for pilots. But this redistribution of fuel to either reduce the sensitivity of the flame to perturbations or dephase the flames relative to each other, those are both very common methods of instability suppression in real engines. And the work that we've done over the past few years has used a lot of advanced diagnostics to understand how they're working, and work with our industry partners to basically help them with better designs for these types of very common suppression methods. The final suppression method is one that's not commonly used, but we hope will become commonly used. And it really goes towards better aerodynamic design for the injector. In particular, we're really interested in how do you design a flow field to suppress the receptivity of the flow to acoustics so that this part of the coupling mechanism never happens, so that the flow doesn't respond to the acoustics, and so it never causes flame heat release rate oscillations. All right, so in order to talk about this and to give you a little bit of a history for the grad students on the line, this is an important story. So I've been thinking about this problem since my PhD about flow receptivity. And so when I first started at Penn State, I came up with this fun project that I thought would be really great for an undergrad researcher. We have a really good honors program at Penn State. So I got a very bright honors student. His name is Ben Matthews. And he was going to work with me for the summer, and he was going to measure vorticity transfer functions. So a transfer function, this is actually a describing function because it's a function of amplitude as well as frequency, but it's an input-output system. You input an acoustic fluctuation, what comes out is a vorticity fluctuation, and I wanted to know how the vorticity response of the flow was going to change with forcing frequency, amplitude of forcing, and the swirl number of the flow. And I'll show you the experiment that we used to do this. So this is going to help us understand this velocity coupling mechanism better. So this is how we were going to define our vorticity transfer function. Is going to be the coherent vorticity fluctuation over the mean vorticity divided by the acoustic velocity input divided by the mean flow. So this is a pretty standard describing function configuration. And I told Ben, go forth and measure. So the experiment he was doing this on is a swirling flow experiment. It's kind of a unique experiment because inside the rig, we can change the swirl number from no swirl up to 75 degrees blade angle, which is a swirl number of almost 2. And so you can get a really big modulation in the profile of the flow, which I knew from previous work I had done was going to change the shear layer response. So we measured a whole bunch of different swirl numbers. So what's being shown on the top row here is the time average axial velocity. These are the swirl numbers. And here is the time average swirling velocity at this black cut line here. So you can see more and more swirl. As you increase swirl, you get this vortex breakdown zone in the middle. And this is on the right, the type of flow field that you'd expect in a gas turbine injector. And the paper that Ben wrote on this work is shown here. This is a really nice paper. So what Ben did was he took all this PIV data, he took it at two frequencies, 600 hertz and 1800 hertz, a couple different amplitudes for 1800 hertz. And what he's doing here is sort of like what we did with the chemiluminescence. At each of the conditions, at each of the velocity vectors, we do an FFT, and here we're plotting the magnitude of the FFT at a given phase across the flow field at the forcing frequency. So the non-swirling jet has really beautiful shear layer response for both frequencies. And then as we increase the swirl, it gets a little wonkier, but then eventually by a swirl number of 1, there was no response. Poor Ben, I thought he had messed up. I made him do these measurements like 3 times. And finally he came back and said, Dr. O'Connor, I am not screwing this up. I promise you, there's just nothing there. And so what he showed me was the pressure spectrum from the pressure transducers inside the nozzle. He said, see, I have the acoustics on. I promise you I'm forcing it. What is this? And so when we did the Fourier transform, plotting the frequency components at these two frequencies, at the forcing frequency, this is very loud. We use police sirens to actuate this combustor. He saw basically no vorticity response, which is what I showed you in the previous slide. And then we plotted it at this peak and we saw this. And I was like, that's what's happening. We were getting a precessing vortex core, which is a very common instability in swirling flows where that big recirculation zone precesses around the central axis, creating a coherent oscillation. So hopefully this video works. This thing screams. Its instability, as you can see, is at about 1,000 hertz. And this is what it sounds like in real life. So that high frequency tone, that's not, there's no flame here. That's not being produced, that's the flow itself making that noise. It's really annoying. But that's the precessing vortex core. And essentially wiping out anything else that was happening. So like any good experimentalist, I need to have friends who do both simulation and theory. And so I told you about my friend Yuan Chuan, who did the simulations for our piloted flow experiment. I have another collaborator, Dr. Santosh Chandra, who is on this call. And so if you ask hard questions about this work, I can just point you over to him. He gave a really excellent one of these talks, I think last year, on a similar topic. But basically we came to him and we said, there's something weird going on here. And so what he does in his group, or one of the things his group does, is linear hydrodynamic stability analysis. He also does nonlinear and other types of analysis. But for this problem, we looked at the linear problem, where you basically linearize the Navier-Stokes equations, and you look at both incoherent fluctuations and then coherent fluctuations, and you look at the impulse response or the coherent response to an impulse input and see how, in this case, we wanted to see how it was growing in space. So I'm not going to go through all these equations, and I know it's super annoying when people throw up a bunch of equations and then don't explain everything, but I also want to leave time for questions. And so this K plus is basically the growth, the spatial growth rate of the shear layer disturbance as a function of downstream distance. So the plus is downstream. And what I'm going to plot in the next plot is this e to the I, this term. Basically, if it's above 1, then this thing is growing. If it's below 1, then it's decaying. So we gave him our data. He was able to apply this framework to the data and at the frequencies at which we were forcing the experiment, was able to see if the shear layer instability was growing or decaying. So like I said, here's that growth or decay term on the y-axis. On the x-axis is downstream distance, and these are all the different swirl numbers that we took data for. And you can see at low swirl numbers, where Ben was actually seeing a coherent response, the shear layers magnify the incoming perturbation, right? The growth rate is positive. Down here, there's no amplification of the incoming signal. We can hit this with, like turn it up to 11 and you see nothing in the shear layer. And it's because the shear layer is not responsive to acoustic forcing. So we presented this paper. So this particular work was done by another undergrad in my group, Mark Frederick. And Mark presented this at Turbo Expo, and somebody asked a really good question, which was, does this depend on frequency? Which was, we looked at this particular case at 700 Hertz. So we did some other frequencies, but we couldn't do an exhaustive sweep. But fortunately, Kieran, who was Santosh's student, was able to do that in theory. And so he looked at a huge range of frequencies, right? So 2 decades, this is Struhal number, which is basically a normalized frequency. And he looked at the max growth rate, so basically the max one of these, for each frequency, and again showed at the high swirl numbers, basically regardless of frequency, you're getting almost no amplification. And so this gave us a really nice reason for why we weren't seeing anything in the experiment, and made me feel bad that I made Ben do his experiment multiple times over. So what this initial work showed us was that there's a real possibility that you could design a flow such that it was not susceptible to acoustic perturbations. And Santosh and I and our teams, in collaboration with Isaac and a few other folks, are looking at how to do this in more realistic geometries. I haven't included all that work yet, but that's coming out soon, and we're really excited about it. So the takeaway from this, I think, before I wrap up here, is that a combination of good experiments and your friends who do theory and simulation can give you a lot of insights into the fundamentals. And then those fundamentals can be translated into actual design. And we saw in the fuel staging and the piloting cases how we're doing that for techniques that are currently used in industry. And in this project, we're taking a new idea and trying to translate it to more realistic hardware. All right, with that, I'm going to wrap up, and I'm really looking forward to taking questions. I have to thank the people with money. So the Department of Energy University Turbine Systems Research Program funded the multi-nozzle work. Solar Turbines funded the piloting work, and the National Science Foundation, my career grant, is funding our work on swirl. I have an amazing team of collaborators and colleagues and students at Penn State. Also want to thank the team at Bangalore, and then Isaac Box at DLR. So with that, I'd be happy to take any questions.
Okay, great. Thanks for the great talk. We've actually got a number of questions from the audience, so I'll just jump into them in the order that they've been received. First actually is from Jay Gore. Acoustic frequency vary between 20 and 20 kilohertz. Is there a subrange necessary to define the pressure oscillations in a combustor?
Yeah, so that's a really good point, and it really depends on your combustor. So actually one of the, I'll put easiest in air quotes because it's still not particularly easy to do, but compared to the rest of this flame stuff, determining the resonant frequencies of your combustor is pretty tractable. So once you know what the geometry is, you can figure out what the frequencies of interest are, but it really depends on the the size of your system, yeah, it really just depends on the geometry of your system, but you can sort of find that out beforehand and then target your experiments at the frequencies of interest.
Okay, great. Next question is from myself. Do you have the capacity to acoustically force the 5-can combustor that you showed? We saw some fuel staging, but can you acoustically force it as well?
We can. And so if you look at work that DOM students who did this work were Mike Zadelmeyer, Jonas Samarasinha, and Alex DeRosa. And if anybody wants those references, I can forward them to you. There is an air siren on that system. And so you can force it between frequencies of about 100 and 500 hertz, up to about 8 to 10% forcing amplitude. Mike Zettelmeyer, who was the first graduate student to work on that experiment, actually did flame transfer function measurements in the 5-nozzle configuration and compared them to single nozzle transfer functions that were taken on the same injector. And so that data is out there for sure.
Okay, great. Next is a comment from Jay Gore. It would be wonderful to have transient pressure measurements, I assume on the 5-nozzle combustor.
Yes.
Based on the time of the talk.
Yes. So that work is out there and in the literature. And if you go to my group's website, which is sites.psu.edu/RFDL, that was actually the goal of the UTSR project, was to look at transients. And so we have transients in equivalence ratio, in staging, and in fuel composition. We looked at transients in the amount of hydrogen in the fuel. And we changed the time duration of the transients, so really fast ramps versus really slow ramps, and the directions. So we were able to look at timescale issues as well as hysteresis issues. And that was a super interesting study that is a completely different talk than this one. But yes, if you're interested in transient behavior, we've done a ton of transient work, and all those references are on our lab website.
Okay, great. Next question is from Johan John. What would happen if only the flame were to be acoustically forced in the setup on slide 10? Would the same roll up be observed? Would the 400 hertz used lead to a different size and shape of the structures?
Yeah, so that work has been done. We did not do it in this experiment, or we might have done it, but we didn't publish it. Work I would point you to there is from my academic brother, Santosh Shambhog. His PhD was on his PhD inspired this experiment. We took his rig and multiplied it by 3. And I think that's some of the nicest data out there on acoustically forced V flames. And the work that he did both with the experiments and then our other academic siblings, people like Santosh, Don Hyuk-shin, and others took that and looked at level set formulations for understanding the growth and behavior of wrinkles on the flame. So we didn't do that work in our group because it had been done by a bunch of folks in Tim Nguyen's group. And I highly recommend, if you're interested in this problem, that set of papers gives you a really fundamental insight into the velocity coupling mechanisms in plug body stabilized flames.
Okay, great. Next questions again for myself. Perhaps I missed it, but are the simulations shown on slide 33 based on LES or RANS? And if it's RANS, does it really capture the dynamics of the combustor?
Nope, that's a really good question. So they are LES,
Okay.
but in that paper, we just looked at time averages and RMS. And so we didn't look at the coherent behaviors, but yes, they were all LES. And I have a bunch of backup slides if people want to look at the way that we did it, but yes, it was LES.
And would you expect a significant difference between the mean and the dynamic behaviors of the flame?
Potentially. I mean, one of the things about that study was we were really just interested in temperature and species profiles. And so, when we first, again, we had the lift data, which I didn't show here, but has been published or is in the process of being published right now. But we were really looking for the mechanism which you can get out of those time average images. In the paper, we discuss a lot about the effect of back support. And a few folks have studied that in swirling flame experiments. In Tim Nguyen's group, Chingo Zhang and Chris Foley did some work on that. Santosh Shambhog now at MIT has done some work at that. The most fundamental work that I think explains this extremely well is Bruno Corentin's work from his PhD at Yale. He used, opposed flow flat flames and did just really beautiful study on how back support works both thermally and chemically. And we were really inspired by that work to help us interpret what was happening in our experiments. So.
Great. Next question is from Santosh. Santosh Androndra. Would you say that the increased mean density gradient in the richer pilots is suppressing the receptivity of the inner shear layer?
I don't think it's a shear layer effect. That's probably second. It's probably happening, but it's probably secondary. And again, the reason that I say that is when you look, I don't have the imaging data in here, and it is in Jihong's thesis though. These pilots at these really low flow rates are just super dinky, and they're pretty, in this injector, they're pretty far from, you know, from the shear layer that's rolling up here. And so based on the fact that we get really good suppression out of very small flow rates, we do think it's a thermal effect more than a fluid mechanic effect, but you're right, there would be some change in shear layer response due to that sort of secondary pathway could be possible too.
Great. Next question's from Sro Young. Hi, Jackie. Is the primary function of the pilot to wrap the flame in the outside oscillation? Then why is it insensitive to the pilot flow rate? Intuitively, I feel higher flow rate has stronger isolation effects.
Yeah, so really, I don't know if I have a flame picture here. So these flames are pretty compact, right? And so like this video is a good example. I think this is 10% of the fuel diverted to the pilot, right? Which is a crazy amount of fuel. You would, this is a NOx factory here. You would not do this. This pilot probably has an equivalence ratio of 1 or something. It's massive. So the majority of the length of this pilot flame isn't helping. Because where the flame's really sensitive to at least the initial perturbations is at its base. And so what we found from both, Jihong's really beautifully designed experiment and then the simulations is that really the region of sensitivity is down here. And so, like I said, you don't need that much of a pilot to help you out. The other thing that's helping you out is the fact that there's a big recirculation zone here, right? And so it's not just, the diffusion of heat and species laterally, but anything you generate along the pilot's going to get sucked back in into the base of the flame here. And so we, in this paper, we also looked at recirculation zone strength at different locations. I don't have it in the slides, but if you look at the paper, we look at the fluid mechanics of this as well, and basically talk about the transport of this heat back to the flame stabilization location. And a paper that is under review for Turbo Expo this year, we look at the impact of the pilot on static stability, so basically flame anchoring, and see pretty similar results. So again, the compactness, and then you're really getting helped out by the fluid mechanics of that central recirculation.
Okay, next question is from Sro Young again. Is Q double dot also important or only Q dot?
So it's the heat release rate that drives the, it's the heat release rate that drives the acoustics. And so I mean, that's the main driver. I'm trying to think like what impact Q double dot could have on, but the main, and I'm really reaching back to my aeroacoustics class when you derive these equations for an acoustic system with a acoustic source from heat release, but you can show that it's Q dot that's the driver.
Okay, next question's from Don Yang. Many thanks, Jacqueline, for the nice talk. On slides 31 to 33, it's interesting to see the effect and analysis of the pilot flame on stabilizing thermoacoustic instabilities. Is this true for all possible unstable modes, or let's say frequencies? And a similar question for the fuel staging case on page 18. Is the conclusion here similar for different potentially unstable modes, or needs to be analyzed separately for different modes?
It's a good question. So in these, So nothing works all the time. And in thermoacoustics, we call that job security. We did not find an example in the multi-nozzle rig where fuel staging didn't work eventually. Wyatt Color, again, if you go to my lab's webpage, Wyatt Color had a paper where he looked at the efficacy of all the different nozzles and what we called I forget, like basically the critical equivalence ratio over which that nozzle would suppress the instability. But at least in our experiment, staging worked all the time. In this experiment with the pilot, it doesn't work. You can even see this from Jihong's data. These low equivalence ratio pilots are making it worse. And you can understand why. If you look at this temperature here, you're actually sucking energy out of that main flame and destabilizing it thermally. And so at least in these cases, these really weak pilots don't help. They can make it worse. We do have some modes in this combustor where a pilot of any level doesn't suppress the instability, and we're doing the analysis right now to figure out why.
Okay, next question is from Amit Sahat Bahar. Thanks for the nice presentation. While hydrogen combustion research becomes popular for gas turbine applications, what do you think about the combustion dynamic problems when hydrogen is used?
Yeah, so that's a real it depends question. So my last student to work on that transient program, the DOE one that I talked about, his name was John Strollo, and he was the one who did the hydrogen composition variation work. And he did his literature review for his thesis, and he came into a meeting and he's like, well, it's split. Half of the people say adding hydrogen makes it more stable, and half of the people say it makes it less stable. So what am I supposed to put in this literature review? And the answer is it depends on the configuration. We found that adding more hydrogen to our particular experiment made it less stable. But that's why these fundamentals are really important. It's not the level of hydrogen that matters. It's the flame shape, the shear layer receptivity, the stretch sensitivity of the flame, right? Like you can translate hydrogen level to these more fundamental coupling parameters and then see why in some cases hydrogen makes it better and in some cases hydrogen makes it worse. But there is, a growing really nice body of research, including by several people on this call, who are looking at hydrogen and the effects that it has on thermoacoustics. So that's definitely of interest.
Okay, next question is from Waruna Kalutaraka. Very nice talk, Jackie. What other chemical species besides OH, if available, that can help to better understand the oscillations in practical systems?
Hey, Waruna, it's really nice to see you, even just through the thing here. Yeah, so we use OH because it's accessible and it, kind of glows like a Christmas tree. And it's, Waruna knows this. I'm not a diagnostic developer, I'm a user. So if I can buy a laser that will do something for me, I'll do it because I'm really interested in the physics. The other species that people have used for this is looking at CH layers, because really what you want to capture is the flame oscillations. Most people aren't doing quantitative lift for thermoacoustics experiments. There are obviously some folks who are, but in general, you just want to track the flame. And so for us, we've been using OH. I think there are some situations where I think, man, life would just be so much easier if I had a CH layer than an OH layer right now. But we haven't implemented that. But basically, you want to look at the regions of high heat release. And so any diagnostic that could do that is helpful.
Okay, we've reached the last question from the audience from Swell Young, and we're getting close to the end on time for today. So the last one is, I'd like to get a better understanding of the data analysis. The FFT seems to apply to the time series of local data, correct? It seems we are not looking into the spatial coherence, structure, and stability. Are those important as well? And if yes, do we do wavelet, POD, etc.? Yeah,
for sure. So yes, all of the above. So for this particular experiment, our first cut is always the FFT, because if you have a really loud instability, there's all the interesting stuff is happening at known frequencies, right? Wavelets are really good in situations where you have intermittency, and some work that my student Ashwini Karmakar has done on the interaction between coherent motions and turbulent motions. She uses a lot of wavelets. We've done wavelet filtered POD. You know, like you can get really, we use spectral POD a lot, the method from Town. And you know, like, so we use all of that in cases where you have to kind of pick out the instability over other stuff going on. For these experiments, particularly in this multi-nozzle case, this thing is screaming so loudly at just one frequency that the rest of it isn't super necessary. The FFT, you know, acoustics are sinusoidal. The FFT is the right decomposition to use. But when you have more complex motions, or you have multiple motions, so all the work that we've done on swirling flows, so this kind of stuff, and again, the work that, if you look again on my lab website, anything with Ashwini Karmakar's name on it, we've been using more advanced techniques because we're looking at sort of how the coherent and the turbulent interact. And so, yes, everything you mentioned is in our toolbox and can be really useful. But my first go-to is always the lowly FFT, because it at least gives you a first cut if you know what your frequencies are.
Okay, great. So that covers all the questions from the audience. So we'll tie off the webinar here. If the audience would like to turn on their cameras and thank the speakers, we're welcome to do. And yeah. Great.
Awesome. Thanks so much for hosting.